Hello everyone. So till the previous video we have seen the zero calculation and we have taken few cases for the zero calculation. Now in this video in starting I will take how to calculate the poles by addition, and after that writing the transfer function that we can write, we have already seen in previous videos. And then we will analyze the frequency means, or you can say stability margins, the phase margin, which is very important parameter here. Okay, so we will see the first and second order system. Anyway, I have written the second order system first and first order system last. Not a problem. We'll discuss both. And effect of right hand side zeros on the PM and why right hand side zero comes, that we will see here. Okay. Yeah. Now the stability, why phase margin should be high. So this is the point of consideration we'll consider. Before that, I want to calculate the pole location. Okay. So what is the pole actually? So we have seen from the transfer function. This is my transfer function. So what we have seen for pole, it should be infinite. So for that, my V out should be infinite for particular given input, which we usually short for the calculation of pole. Okay. Let's first take the simple example. What is my GM cell? My GM cell is nothing but a current source. Okay. So my GM cell is a current source. And this current is fed into some capacitor CL. And what I want here, V out. And what is my this current? Current is nothing but GM V, and this is my GM cell. So what can we write? Can we write directly as V out is nothing but when this current is charging my capacitor, so CLS. What we can write from here? GMV in CLS. So my transfer function comes is, GM by CLS, and this thing we have seen from the calculation of GM cell itself. Okay, so this is what the ideal current source actually. So it is for ideal current source means R naught is infinite for this current source. What I mean to say, my GM cell is nothing but who is generating a current. So this current is nothing but some quantity, that is GMV that I am generating. And if this current source is practical, let's say, then there is what? There is some R naught. So ideally we consider R naught infinite, but practically for the current source, this R naught is not infinite. So what we have done here, we have seen that this current GMV in is going in two ways. What is the one way? One way is my this V out by R naught. What is the second way? Second way is CLS. Okay. So what we can see from here, we can see my current is going in two ways. 1 upon R naught, I'll write it as G naught, and second thing is CLS. So what is the transfer function? We can write the transfer function as V out by V in, what we have written. Okay, so transfer function comes as what? GM G naught plus CLS. G naught plus CLS. So what we can see here, if you take the G naught common, then we have, sorry, this is G naught. Okay, G naught 1 plus CL by G naught S. Okay, so from here, what we have seen, we have DC gain and 3 dB frequency, which is the pole frequency, or dominant pole frequency. Here also, no pole, no second pole, and zero is visible yet. Okay, so my point is, for any in general current source, what we are seeing, okay, I modeled what? GM cell is nothing but a current source. I told this thing initially, which is a controlled current source, voltage controlled current source. It's because its current is nothing but GM in. This I is nothing but GM in. So this current is a voltage current, means current controlled, sorry, voltage controlled current source. So now if I want to use the intuition, what I told, for making for calculating the pole frequency, I want R out at this point and I want C out at this node. Okay, And my motivation is to get what I have to get. I have to make my V out infinity. So how can I make V out infinity? We need to calculate R out, and this R out should be what? This R out should be infinite. Then what we can say, V out is nothing but some sort of current flowing through this R out will give me infinite magnitude of the V out. Hence that particular location will give me the pole location. Okay. So ideally what we are seeing that there is means ideally when we look this side there is a no impedance, or you can say infinite impedance. Okay, so ideally we can say the R out is what? Okay, not R out exactly. What I will say, R out effective, or better to say, Z out should be is infinite. Z out should be infinite instead of R out, because R out is a finite quantity, so it is not infinite. Whether it is infinite here, the point is that we should make the Z out to be infinite for making the V out infinite. Instead of writing this R out, I should write Z out. Okay, so R out here is infinite. What mean to say Z out to be infinite means Z out is what? R out parallel with 1 upon CLS. Okay, so it to be infinite. It means what? Because R out is infinite, so I can say 1 upon CLS to be infinite. Okay, so what I mean to say, because R out is infinite, so two ways are there. Whether I can write the complete Z out to be infinite. So what is the Z out from here? Z out is my R out parallel, because R out is this impedance. This is Z out, but R out is this impedance. R out. So what is Z out? Z out is nothing but R out parallel 1 upon CLS. As R out is infinite, so it is effectively 1 upon CLS. And when you will make this to be infinite, what you see? S should equal to 0. So S is 0 is nothing but pole frequency, which is called as dominant pole frequency. I think the concept is clear. If there is any confusion, we will take few more circuits here. Okay, so there are two ways. Directly you can write R out at particular node and C out at that particular node. And the pole frequency will be what? 1 upon R effective, better to say R out, or at any in general node, I will say it is R effective at that node, and for any in general node, I will say C effective. So I can write R effective times C effective. Okay, so this is the pole frequency in general. Okay, yeah. So this is for we have seen from the transfer function also, but transfer function for ideal case was coming as this. So what is the pole frequency? The pole frequency was s equal to 0, because only at r equals to 0 transfer function is infinite. It means our v out is infinite. Okay, so this was the pole frequency. So now if you take the practical current source, which is a GM cell with output impedance, then what I will consider? I'll consider this is my R naught and this is my CL. So I have two ways to make my V out infinity. Okay, this is my I. So I have two ways to make my V out infinity, not two ways. What I will say, I will calculate two things. One thing is that R out, one thing, and C out is other thing. And directly these are the effective values of resistance and capacitance at that particular node. So my time constant is nothing but R out C out, or R effective C effective. Then we can directly write the omega P is 1 upon R out C out. Okay, when we calculate the R out, we are not worried about this CL. Okay, so I'll keep CL apart from here. So I'll open the CL, better to say open the CL, and I'll calculate the R out. So what is the R out? We can see the R out is taking the parallel. So this I is okay. This I is what? This I is your okay. Then this I is open. So what we can see, any in general independent current, we make it open. Why we are making it open? The reason is being because V in is 0. We are making the V in 0 for calculating the R out. So it is not I am opening because it is a ideal or it is a dependent or it is independent. It is not an independent. Actually, it is a dependent current source. But why I am opening it? Because the I is your GMV in. Because I is my GMV in, and as V in is 0, so my I is open. So I can say like this. So what is the R out? R out is nothing but R naught itself. Okay. So now the second thing that I want to calculate here is C effective at this node. Okay, so when I'm calculating C effective at this node, then what I will do, okay, instead of saying R out, I will say C out. What is the C effective? This is my I, and this is the parallel unknown. Okay, so in that case, I'll say that C out is effectively my CL. So what is the pole frequency? At this node, when I am worried about the CL, I will not consider my R naught. Okay, so what is the omega P? Omega P is 1 upon R out. Okay, so this is the one way when we calculate the effective impedance and calculate the effective resistance and effective capacitance at particular node, we can write the pole frequency there. Okay, so when we calculate the effective resistance, we are not worried about the capacitance at that node, and when we are calculating capacitance at that node, we are not worried about the resistance. Or this thing we can write also like this. So when I'm only looking for my capacitance, I will not worried about what is my okay. So I will not be worried about the this impedance. So what I can see also for this I can write directly. This is my node where I have some sort of capacitance and nothing is here. I will not consider anything this side. So when I consider C out at this node, I will say it is a only CL. So this is the one way. The other way of calculating pole is when pole comes. Okay, we will see this thing. So when pole comes, actually this is my question. So pole comes means my output should be infinite. This is the point. Or mean to say HS should be infinite. Okay. Oh yeah. So what we can see, if there is any impedance Z, so I'll draw it first. So this is my input. This is my Z1. This is simply Z2, and this is my output. So this is a very fundamental network that I will say it is a voltage divider, and I am getting output. So this is my circuit. Now what is my target? My target is to get output to be infinite for given V. So what is the point? We'll see that first make this voltage source as a zero, then calculate Z out effective. Okay, then do what? Make this Z out to be infinite, and once this Z out is infinite, my V out is infinite. So this is the procedure. So now what I will do, the first step I will take. So these are the number of the steps that I will do. First step, second step, third step. So with these three steps, we'll get the pole. Okay. So when we make the V out to be short, sorry, V in to be shorted, this is my Z1. V in to be shorted means it is shorted. Okay, so here I'm not worried about the V out. I'm rather worried about the Z out because my target is to make the V out infinite, and V out we know it. That V out is nothing but I times some sort of I times Z out. So if Z out is infinite, my V out is infinite. Okay, so what is the Z out here? As this node is also shorted, so I will say this is nothing but a parallel combination of Z1 and Z2. So what it comes? It comes Z1, Z2Y, Z1 plus Z2. So when it is possible to make my Z out infinite, to make the Z out infinite is the only possible condition, make denominator to be 0. In that case, what will happen? Z1 should equal to minus of Z2. So what we can conclude here, if both Z1 and Z2 are resistive, above consideration is above consideration doesn't hold. Above consideration doesn't hold. Okay, why it doesn't hold? Because it is not possible that my if Zn is sorry Z1 is nothing but R1 and if Z2 is R2, it is not possible at all that Z1 can be minus Z2. This equation doesn't hold actually. Two resistors are like a positive quantities, so saying this is incorrect me. Okay. So what we can see from here, these two cannot be resistors at the same time. We have seen from our circuit as well. What my dependent current source was saying, dependent current source means my GM cell was saying this my Z1 what? It was my nothing but R out, which was the impedance of my or we'll say this was nothing but impedance of my current source, which is nothing but V in times GM. Okay, so this was this. Okay, and what was my R2? Z2? Z2 was my capacitor. Then we could do this. What was my Z out here? So what was my Z out? I can make this open. Where V in is zero, so I can make it open. Means this current source I can make it open. So let me highlight this thing again. Okay. So what we'll do, as my Vin is zero, so I'll make this current source to be open, and then this R out will behave as the Z1, and this CL is working as a Z2. So overall, we can write the Z out expression. Okay. So overall we can write the Z out expression, and from the Z out expression, we can put Z1 equal to minus of Z2, then we will have the pole location. Okay. So this is the point that I want to make here. Yeah. So what is my Z1? My Z1 is nothing but R out, which is the output impedance of my current source, which is the GM cell, and Z2 is my 1 upon CLS. Okay. So from this, we'll say that Z1 is equal to minus of Z2. So from here, I have this S equal to minus of R naught CL, which we have seen here. Okay, so what is the pole? Then my omega p is nothing but 1 upon R naught CL, which also called G naught by CL. We can see this thing from our transfer function as well, what we have seen here. You can see from here as well. What is this? This omega p is nothing but G naught by CL. Okay, which is same as what we are getting by intuition analysis by the intuitive analysis of pole calculation. I'll take few more examples, then we'll proceed to the exact GM cell again. Okay. So now I want to calculate this pole again. Then what? This is the condition that. Okay, so this is the condition. Then make this arrow to be infinite. Okay. Now let I give you the structure. So let's say this is the R, this is the C, this is the R, this is the C. Okay, and I want to calculate the poles here. Here is my V in and here is my V out. This is a general structure for pole calculation. So what is the motivation? This I will consider as Z1 and this I will consider as Z2. So overall I can reduce my diagram again to Z1 and Z2. So what we will see, we'll see just again we'll make z1 equal to minus of z2 condition to hold, and we can see we can find the poles. Okay, so the same thing we'll apply this directly to this particular diagram. So what is my z1? Z1 is nothing but r parallel of 1 upon cs. So it can be written as what? R by 1 plus rcs. Okay, what is my z2? Z2 is nothing but r plus 1 upon cs. Okay, so what is my point? My point is to make this thing, this equation to be whole. So what is this? This is nothing but 1 upon sorry r upon 1 plus cs minus r minus 1 upon cs. So how it can be written as, let me a little bit solve it more. It is 1 plus rcs by We can write it as CS. It's fine. Okay. So then what will happen here? I'll write it here RCS, and here we'll write as minus 1 plus RCS and 1 plus RCS. So what we can see from here, if we open it, we can see, let's take the minus this side. So 1 plus RC, S plus RC is 2 RCS plus RC square S square. So from here what we'll get exactly, we'll get RC square S square plus 3 RCS plus 1 equal to 0. So from here what we got here, we got a second order equation. What we got? We got second order equation. Why we got the second order equation? Because there are two energy storing elements. Because there are two energy storing elements, two energy storing elements with independent independent state variables. What it mean, independent state variables? So actually, when there are two capacitors in such a way that they have initial conditions independently set. Okay, if I call this is V1, this I call V2, then there is a no relation between V1 and V2. And such other way, if they are like this, like let's say C1 is this, and this is my C2, and suppose there is other network like whatever the R or something else, then what we can see, this if this is my V1 and this is my V2, and it is my, let's say, V in, then what we can say, my V2 is nothing but V in minus V1. So I will say V2 is not set independently. It is dependent on V1. So only one state variable is there in the second case. But in the first case, in this case, there are two independent variables, there is a one independent variable only. So whenever this particular combination comes, then one state variable means only one pole will be there. Two state variables means two poles will be there. From V into this V2, you can see these V1 and V2 are independent. Okay. So we can see from here also, because they are dependent state variable. So only one pole is there. This thing we can see. This is my C1. This is my C2, and it is my some R naught. I am capturing my output voltage here, and here I am giving my input. So when we will calculate the pole, what we will do, we will see Z1 equal to minus of Z2. We'll do like this. This is the fundamental. But what we are seeing here, when we make our V in 0, which is the first step, and we short it, what will happen? Actually, the circuit will reduce to two capacitors in parallel. So this was the thing that they only one state variable or only one independent variable means your entire cap combination is reduced to one cap. Means two caps are now reduced to one cap. So my Z out will be what? It will only be, this is called the C equivalent, which is nothing but C1 plus C2. So my Z out is nothing but R out parallel 1 upon C equivalent S. So overall I can say this Z out to be infinite means Z1, which I call R naught, equal to minus of Z2, which is nothing but C equivalent S. So X comes out 1 upon R naught C equivalent, which is nothing but minus 1 upon R naught C1 plus C2. So, okay, it is only single pole. Only single pole. So, in this first set, it looks like capacitors are there, but only one pole means two independent variables are not there. Two independent state variables are not there. Okay. So I think this is enough for the discussion of the pole calculation. Now we will switch to okay, so now we will switch to this phase margin and the gain margin, whatever, not a gain margin required here, phase margin, and what the effect of right hand side zero here. Okay, so this is the discussion of calculation of pole and zeros by intuition we have seen in the previous in this video. Now we will move to what one initial transfer function was there. Actually, when there is zero, this is z naught and sorry, a naught sy omega z 1 plus sy omega p1 1 plus sy omega p2. So what we ideally considered, we have seen the single stage op amp was nothing but a first order system. Okay, initially we have seen the single stage op amp, which is a GM cell with capacitive lobe. Single stage op amp is an ideal integrator. Okay, so it is an ideal integrator. Means one more thing, it is a first order, or it is a first order system. It is a first order system. We can also see ideally its transfer function should be what? Its transfer function should be some sort of GMY CLS that we have seen, and practically its transfer function was coming out when I considered the G naught means R out of GM cell, then it was coming out as CLSY G naught. Okay, so here we can see the some finite pole frequency was coming and some finite DC gain was coming. Okay, so overall we can see this is the first the both are the first order system. Okay, so actually for this the body plot we have seen, it was some sort of with the infinite gain, and it was some sort of constant, then some movable gain. Okay, so this is my 3D frequency. Yeah, we have seen this thing, but what we are seeing here for the GM cell, this is also the possibility omega z, and omega z is non-zero value, and omega p2 is also a non-zero value. So this is making my system of higher order, which is actually degrading my phase margin. Okay, so what are the other poles and zeros are doing there? Okay, so yeah, other pole and zero are making or deviating the op amp from ideal first order characteristics. Ideal first order characteristic, which is required for which is required for ideal integration, which is the fundamental thing for this op amp. The integration should be ideal. Okay, so what we expect that what is the problem actually? Problem is that they will degrade the phase margin. They will degrade the phase margin. So the problem is that this is the problem. They will degrade the phase margin. How they will degrade, we'll see. Okay. So what ideally should be there? This omega p2 should be very higher than the omega p1, and omega z should also be very higher than the omega p1, so that we can approximate it as a so that this transfer function this transfer function can be approximated can be approximated as a first order system, which is the desired requirement for us, first order system. So this is my requirement. Okay, so these are the assumptions that we make here. So overall. So if for this higher order system, let I should write here 1 plus sy omega z, 1 plus sy omega p1, 1 plus sy omega p2. Let So ideally what we expect, my omega p2 should come after omega ugb, or omega z should also come after omega ugb at least, so that I can have the first order approximation till UGB, which is nothing but a characteristic of my of my ideal integrator, which is the UGB sum frequency, and this is my omega P1, which is a 3D frequency. This is my DC gain. Okay, so this is the bare minimum requirement for us. And after that, a pole is coming, I don't have any problem. If after that pole is coming and after the zero is coming, so it is not my problem. Okay, but ideally we want is these two things, which is nothing but omega p2 and this is omega z, they should be at least greater than or equal to omega u, so that our system can be approximated first order system at least till the at least till the UGB frequency. Okay, so this is the bare minimum requirement that I want. So if this particular pole P2 comes before this omega u, then what will happen? And this omega g comes before the UGB, then what will happen? We have to see this thing. Okay, so if this thing comes before, if omega P2 is less than omega UGB, this is my first consideration, and let omega g is still after the omega UGB. So for this case, we have to plot the Bode plot, and then we have to see and what is the problem. And second thing, we'll calculate or we'll plot the Bode plot for these both conditions. Omega P2 is also less than omega UGB. Omega G is also less than omega UGB. Okay, so these are two things. So first thing I'll see, if my omega P2 is less than omega UGB, then what will happen actually? We'll see. This is my omega. So this is the decision. After that, this is a pole 1. This is my pole 1. And if the pole 2 comes like this, so this will be omega P2, which is a minus 40. This is my UGB, and after that, let's say the 0 comes. Okay, so this is my omega Z, and in between there is, so this is my omega UGB. So what we have seen, if I draw the phase plot, and what we can see, the phase 1 initially is 0 and it was settled, and before here it was little low, and after that it is little increasing. Okay, so some sort of means I am somewhere here at around the UGB. I am somewhere at this point. So what is mean to say, if my pole is coming before UGB, then we'll see this phase margin requirement. Okay, so what we can see at UGB, what is the phase at omega UGB? It is negative than this minus 90 also. Okay, so at first pole frequency it was somewhere around minus 45, and after that it was about to reach minus 90, but it is more negative. So somewhere it was expected to reach the minus 90, but let's say it is a minus 120 degree, let's say, for this particular case when the omega p2 is less than that. So what will be the phase margin? Phase margin is nothing but 180 plus this phase, which is minus 120, let's say, so it is now 60 degree. So it is looking good, but what we have seen, If my first order system is approximated till the UGB, then what was my phase margin? My phase margin was minimum 90 degree. Now the phase margin reduced to 60 degree. So reduction is phase margin. Reduction in phase margin, uh, stability is decreased. Stability is decreased, or can say stability margin is decreased. Stability margin is decreased. If the further phase margin reduces, we will reach to some instability, or can say we will have some peakings, which is not I am covering here. Peakings will come into the response. Peakings. And what are the peakings? Just I should cover for sort of the discussion here. If there is a step response, what we see? Ideally, we see the okay for the sluggish response, it is like that. And when we are approaching to the and when we approach to the critical system, then what will happen? It will go faster and it will settle. And after that, more reduction, what will happen? It will some peaking will come, then it will settle. Okay. So what we will see when the phase margin is less, some sort of oscillations or oscillation will not happen, but we can say yeah. So this is the in-depth story when we exactly look at the pole frequencies and what are this sort of like exact inside means frequency response. We will see how the speaking is occurring, but overall we will see what we want. We want that my output should settle to some steady value with a smooth like not there should not be any ringing, peaking or ringing I should say. There should not be any ringing, peaking or ringing. If there is a step response, then there is some possibility some sort of this is settling behavior. So I don't want this. It is not required. It is not expected because it is a sort of error. Because it is a sort of error. So this is the in short I want to tell why my phase margin should be as more as possible. So as much as PM is less, as much as PM is less, more and more ringing is there. Ringing is more or peaking occurs. Ringing is more, some sort of peak will occur, then our response settle after some sort of ringing. Okay, so we want more phase margin. Okay, so this is the story till now. In the coming video you see what is the exact equation for the phase margin and how we relate and where should be the location of p2 omega p2 and where should be the location of omega z. Minimum they should be omega ugb, and why they are required, so that we can have the first order response till the omega ugb. Okay, and if it is not like that, then what is the possibility, then we will see here. Okay, so thank you for this video. We will see these things in coming video.